It is distinct honor to introduce Professor George Ellis. Professor Ellis is the Emeritus Distinguished Professor of Complex Systems at the University of Cape Town and one of the world's leading theorists in cosmology and general relativity. He is the co-author alongside Stephen Hawking of the seminal monograph, The Large-Scale Structure of Space-Time, which established the rigorous mathematical foundations for understanding black holes, singularities, and causal geometry of the universe. A fellow of the Royal Society and past president of the International Society of General Relativity and Gravitations, Professor Ilse has been instrumental in defining the physical laws that govern the cosmos. Beyond his contribution to physics, Professor Ellis is a profound thinker and deeply questions the validity of reductionistic framework with his theory of top-down causation. He demonstrates how complex systems, including the human brain, can causally influence underlying physical matter, providing a scientific framework for understanding agency and ethics. A recipient of Tem- Templeton Prize and the Order of Macbungwabe, sorry for pronunciation, from the South African government. Professor Ellis is a leading moral voice in science, advocating for the synthesis of rigorous empiricism with a deep appreciation for the philosophical and ethical dimensions of human existence. His lecture, The Nature of the Universe, the Big Picture, invites us to step back from competing models and reflect on the boundaries of scientific explanation itself. Professor Ellis, it is a privilege to have you with us. This virtual platform is yours now, sir.
Thank you very much. Great pleasure to be with you. So our ancestors look up at the sky and ask questions about our existence. And the questions are, what are stars made of? Why do some of them move? What's the nature of the Milky Way? And are we at the center of the universe? And how did it come into existence? And all of this I used to ask. And this was before we knew the distance of the Milky Way, before we knew that the Milky Way was a whole set of stars. And this is this beautiful picture of the astronomer trying to look out and find out the way it works. Now, I'm going to have three parts to this talk. First, I will summarize the current canonical understanding of the physical nature of the universe, together with their limits. Second, I will reflect on the limits to knowledge about the physical universe. And third, I will consider some issues that go beyond what science can say, and including what kind of meaning is there in the universe. So the universe has physical elements that are understandable through physics and through astronomical observations. I'm going to summarize here the current canonical understandings of the physical nature of the universe, together with their limits. And some of your other speakers will question this canonical, but I'm going to present the canonical. The physical evolution of the universe is based on testable physical laws. It's very important they're testable. The physical laws deal with the interactions of particles and fields, and they're tested using laboratory experiments and particle colliders. Together with observations of what exists, inter alia, by using telescopes of many kinds, these laws enable us to our understanding of the physical universe. So the universe is made up of galaxy. Galaxy is billions of stars, and the Milky Way is a galaxy seen edge on. Galaxies come in clusters, and a typical galaxy, this is Andromeda galaxies, 100 billion stars, about 50,000 light years across. This is very similar to our galaxy, and if this was our galaxy, we would be way out towards the edge over there. The Earth to the Sun is 8.3 light minutes. Proxima Centauri, the nearest star, is 4.3 light years. And so this is 50,000 years, immensely larger than the Earth to Sun or the distance to the nearest star. Now, the universe is evolving with time. Observations of distant galaxies establish that the universe is changing with time. Its overall scale is increasing as galaxies move away from each other. All the greatest minds at the time, from 1917 to 1931, assumed the universe was static. And this was Einstein's greatest mistake. Einstein denied that the universe could evolve. And this truly was his greatest mistake when both Friedman and Lemaitre told Einstein they had evolving solutions. He told them that those were non-physical. The evolution of the universe is governed by the laws of physics, which are the same everywhere and unaffected by our existence. We can't change these physical laws. And the evolution is governed by gravity, Einstein's theory of general relativity. Now, this need not have been the case. This is true because stars and galaxies are uncharged. They have no electric charge. If they did have electric charge, then electricity would govern the evolution of the universe. But because stars and galaxies are at large scales uncharged, then Einstein's theory of general relativity governs what's happened in the universe. The outcomes depend on what matter and radiation is present. And here's the evidence that the universe is expanding from Hubble in 1929. He measured a series of distant galaxies. He measured the K and H lines in the spectra, and he measured the distance given by apparent size. And he showed that that these lines are shifted because of the Doppler shift, because they're moving away from us. So this was evidence that the universe is dynamic, that the larger the Doppler shift, the smaller the thing looks, and therefore the further away it is. Larger distances correspond to larger velocities of recession from us. Now, the concordance model looks like this, and you've all seen this map, and I'm going to step through it step by step to see what happens. Time is going sideways. The start of the universe is over here, and the physical scale of the universe is represented sideways in this picture. Now, there was some kind of start, and I'll return to talk about that. Immediately after cosmic inflation took place, an incredibly short period after the start, the universe expanded hugely by more than 70 eFols, became very empty and cold. Then reheating happened, conversion of the inflaton field to matter and radiation, and that all took place in a very, very short period of time. Matter and radiation then cooled down, and Big Bang nuclear synthesis took place at about 10 to the 9th degrees Kelvin. Baryon acoustic oscillations took place later, the whole universe acting as a great oscillator, and these both affected structure formation. And Le Havre gave a wonderful talk about all of this an hour ago. Primordial nuclear synthesis took place, in which you get neutrons, hydrogen, helium, tritium, helium-3, beryllium, and lithium through this series of reactions, and they resulted in primordial element abundances of deuterium, helium-4, helium-3, small amounts of lithium, beryllium, but no heavier elements. So the elements out of which we are made did not come from the early universe. This is a form of downward causation from the cosmic temperature-time relation. As the universe expands, the temperature decreases with time, and that's determined by the cosmological density of matter, and which is rho t. And this is a downward causation from this cosmological scale interaction down to the scale of nuclear physics, as shown in that diagram. Then, as cooling took place, the ionized matter became neutral, and matter radiation decoupling took place. Before this, matter and radiation were tightly coupled. After that, they were decoupled. And black body radiation was emitted at a temperature of 4,000 degrees Kelvin. And this temperature decreased inversely with the scale of the universe. So this is when the black body radiation was emitted after about 300,000 years after the start of the universe. And one of the most remarkable diagrams which we have is this one, that the spectrum of that black body radiation has been measured, and the spectrum is a black body spectrum to more accuracy than you can see. The errors are less than the size of this line. So black body spectrum at 2.73 K, a spectacular agreement between theory and observation. And what this proves is that both quantum physics and statistical physics held unchanged at that very early universe. And so this confirms that physics was the same at that time. Now, the isotropy of this radiation, at 1 part in 250, it looks exactly the same in all directions. Which is evidence of smoothing of the universe on the larger scales. This is an all-sky map here, and if we assume we're a typical cosmologic observer, so all observers see the same, then it's a theorem that the universe has a Robertson-Walker geometry, which is the standard geometry of an expanding universe. If you go to 1 part in 250,000, at 1 part in 1,000, you see a cosmic background radiation dipole. It's hotter in one direction and colder in another direction. And we interpret by saying we're moving relative to the fresh frame of the universe at 370 kilometers a second. So there's a standard of rest in the universe due to its time-dependent Robertson-Walker geometry. If we remove that dipole, then at 1 part in 250,000, we get these very, very small fluctuations. This is the entire sky. It's an image of the last scattering surface, a temperature variation over the entire sky when we've taken out the dipole. And it's a series of very tiny fluctuations, and these are the seeds of structure at later times. So this is these fluctuations are 1 part in 100,000. This is the image of the last scattering surface. And it's basically random Gaussian fluctuations, which are the seeds for galaxy formation. Now, you can analyze the angular variation of here, break this up into different angular variations, and you get this remarkable series of peaks. And peaks in the angular power spectrum are due to inhomogeneities at different scales in the hot Big Bang era. And theory and observation agree extremely closely. The observations are the dots and these lines, and the theory is these curves. And it is a truly remarkable thing that the theory and the observations agree. It's a great triumph of cosmological theory, and this gives us confirmation that our theories are at a large scale correct. These fluctuations, then there were dark ages when as the black body radiation cooled down and there weren't any stars, but then the first stars, these are the dark ages, the first stars formed, and then galaxies, planets, and all the rest forms at later times. Fluctuations on the large scale surface led to structure formation through gravitational instability. To do so successfully, an agreement with the cosmic background radiation required both dark matter and dark energy. And again, Professor Le Havre mentioned both of these, and I'll come back to them again. The fluctuations originated through quantum effects, quantum fluctuations in the inflationary era. And one of the things which is missing in the standard theory is how those quantum fluctuations become classical. And this is one of the great big scandals in the standard model. There were quantum fluctuations, they weren't classical. By the time you hit the last scattering surface, they are classical. And how that transition took place is a missing element of the standard model. Now, then stellar nucleosynthesis took side and side stars, and in stars you had this onion structure of shells. Hydrogen, helium, outside helium, neon, then helium, carbon, neon, oxygen, carbon, oxygen, neon, magnesium, silicon, and then iron and a nickel core. And this is one of the triumphs again of theoretical astronomy, is finding out that all of these nuclear reactions were taking place inside the star. This is a massive star near the end of its lifetime, where it has this onion-like structure just prior to expanding as a supernova. This is again an example of downward causation. The temperature, density, and fractions of elements vary with radius at the macro level. They determine outcomes at the micro level. So they're different nuclear reactions at each radius. And this is an example of what's happening at this particular radius. And so the macroscale structure is determining what nuclear reactions took place at the microscale. The first generation stars create elements up to iron and nickel by stellar nucleosynthesis. And some of these ended their lives in massive explosions, spreading these elements through space. Second generation stars formed from this debris. They had accretion disk around them containing these elements. These led to the existence of planets, which contained the key elements of life: carbon, nitrogen, oxygen, phosphorus, which had been created inside those stars. Hence the famous phrase, "We are stardust." Now, so you had all of this taking place: stars, phalanx, galaxies, planets, and so on taking place. First generation stars, second generation stars, and then eventually the speeding up of the universe, the dark energy leading to accelerated expansion. And this was discussed in depth in the first lecture this afternoon. A completely unexpected anti-gravity effect, because ordinary gravity always causes things to collapse. Here, something was making it not collapse, and that was dark energy or cosmological constant. And the evidence here, the supernova cosmology project, this curve isn't straight, it was expanded to bend down, but it actually bends up. So the late time speed up of expansion must be called some form of dark energy, which may change with time when it's called quintessence. Or it may just be the result of a positive cosmological constant. And at present, that's a viable option. So this is distance against redshift, and it's the curve is bending up when we expected it to bend down. And this won the Nobel Prize towards the end of the last century. The present-day age of the universe is 13.7 billion years since it started. And this is big enough that there's no age problem for stars and star clusters. One of the major things you have to do in cosmology is check that your theory of stellar formation doesn't result in stars having a bigger age than the age of the universe. And for a long time, in fact, this was the case, because the Hubble constant was wrong by a factor of more than 2. And so for a while, we actually had a situation where cosmology was inconsistent, because some of the stars clustered were supposed to have an age bigger than the age of the universe. Now we have recalibrated the age of the universe, and there's no longer this problem. Now, if the age now is 13.7 billion years, so what will this diagram look like at 18.7? What will it look like in another billion years? And the answer is, this right-hand edge of this diagram will have moved a billion years to the right. In other words, we live in an evolving block universe, a space-time which has a future edge, and that future edge is moving with time. And at present, from the start to here, it's 13.7. In a billion years, it will be 14.7 billion years old. So at later times, the space-time itself is extended. It is larger than it was at earlier times. Now, what will happen in the future? Will it keep on expanding, or will it collapse? Well, will it collapse to infinity in a finite time, which is called a big rip? As far as I can believe, I don't think there's any likelihood whatever that it will collapse, because the dark energy is far too large for that to possibly happen. What is likely to happen is the universe will just keep expanding forever. It won't expand an infinite amount in a finite time, which is called a big rip. I think that's completely unphysical. Almost certainly neither will happen, the collapse or the big rip. Almost certainly it is likely fated to extend forever, with the temperature going to naught, which used to be called the heat death. So we have a very successful database model. All the observations converge to the same set of cosmological parameters. They lead to the lambda cosmological cold dark matter standard model of cosmology. in which the universe is very nearly spatially flat. Energy density is 71.4% dark energy, 24% non-baryonic dark matter, 4.6 baryonic matter, and the age 13.8 billion. Now, non-baryonic dark matter, this was very, very unexpected as well. In order to make, this is required in order that the structure formation studies and the microwave background studies fit together, and they do fit together pretty well, provided you have the dark matter. And this is matter which does not interact with baryon, which is why it's called dark matter, because you can't see it. It only interacts gravitationally. So, multiple issues. The big five issues is what's the nature of dark energy, and we simply don't know, and that was discussed at length. Now, one of the things which our theory should not allow, that should be allow W less than -1, negative inertial mass density, and many analyses of dark energy, in fact, allow W less than -1, which is that the density plus pressure is less than -1. Now, to my mind, that is completely unphysical and cannot happen in physical reality. So in my mind, when you're examining the nature of dark energy, you should forbid anything to happen like that, because that's unphysical. You should exclude that from your analysis. Now, what is the nature of the invisible dark matter? And it's not ordinary matter, and we simply don't know what it is, and a great many examinations are taking place to see that. What's the nature of the inflaton that powered cosmic inflation in the very early universe? And we don't know. And we've actually got about 200 models of what the inflaton might have been. So these are the big three. Now, then why is there an inconsistency between the near and far Hubble parameter estimates? Is it a systematic error? Do we need modified gravity or inhomogeneity? And we simply don't know which of these the problem is. So there is a problem. It's not enough to say, it's not a big enough problem to say that the whole model is wrong, but there are various possible ways that this could be resolved. It might be a systematic error in the measurements. It might mean we need modified gravity. It might mean we need inhomogeneity, make an element of inhomogeneity to make everything work. And what this emphasizes the need for consistency tests of the standard model. One of them is, is a perturbed Robertson-Walker geometry actually a valid description, or do we need an inhomogeneous model? And there's a test which I made up, which I discovered with John Baldwin many years ago. I mentioned the dipole of the microwave background radiation. There has to be an equivalent dipole in all measurements of number counts. And if that equivalent dipole doesn't exist, then something is wrong with the standard model. And the final problem is, how did galaxies and black holes form so early in the universe's history? And this is a big puzzle. With the James Webb Space Telescope showed that we have galaxies and black holes very early in the universe, and it's a problem how they formed so early. Now, there are many unknowns in addition. The first is, what's the spatial curvature? Is the universe positively or negatively curved? And many analyses don't even try to determine what this curvature is, but it's a key parameter. If the curvature is positive, then the universe closes up on itself, and it has a finite amount of matter, a finite amount of galaxies, and it closes up spatially. If it's positive or negative, that's not necessarily the case. If it is closed and so finite, what's its topology? And there are many possible topologies for the universe. It can have a torus topology, a Möbius strip, many more complex topologies, and a lot of work has been done looking at what the spatial topology of the universe might be. Even more fascinating is the possibility that not only is this universe spatially closed, but it's closed up on a scale small enough that we have already seen right around the universe. We've seen everything that there is, and that's a testable possibility. If we lived in a small universe, that is one which closes up on itself on a scale smaller than the visual horizon, we could have seen our own galaxy as it was multiple times in the past. And I would really love it if that was the case. Unfortunately, it doesn't seem to be the case, but that is a possibility which you should be aware of. And then finally, do we need a multiverse? and some other people are going to talk about that in this series of lectures. The only point I'm going to make, it's not observationally provable because of horizons, which I'll mention in a moment. And some people even say there are billions of identical copies of you out there, and that simply is totally improbable. Now, the point about this is there are limits to data about the physical universe. This is the section of my talk. There are a variety of limits we can know about for a variety of reasons: the uniqueness of the universe, its vast size and scale, and the existence of horizon. Cosmology is unique about the sciences because there's only one universe. And by definition, there's only one universe. By definition, the universe is all that exists, or let me be more precise, all that exists that is connected to the bit of the universe that we can see. If there's completely disconnected universe, that's irrelevant because we can have no causal connection with them and know nothing about them. Now, we can't do experiments on the universe per se. We can't rerun the universe with the same or different starting conditions to see if things work out. Now, in most physics, you rerun many copies of the same thing and see what happens, and then you can get laws of what happens. We can't do experiments on the universe. It just is what it is. We're inside the universe, and we're not able to run experiments on the universe. Furthermore, we can't compare the universe with any similar objects, as we can in the case of mountains or stars or galaxies or elephants. In those cases, there are many similar things, and you can form statistics of those things by looking at a whole set of them. There's only one universe for us to observe. We can make many observations of that one universe, but they're all observations of the same single universe. And these are reasons why the universe of cosmology is different from all the other sciences. It's because the universe is unique. There isn't any other universe by definition, at least not one we can interact with. So it doesn't even make sense to talk about laws for the universe that some of my colleagues do. The very nature of a law is that it applies to multiple objects. All apples at the same place fall to Earth at the same rate. All planets move in elliptical orbits and so on. There's no other universe to which such a law can apply. And if there was a law, you could never prove that it was such a law, because you have to observe multiple examples of the thing to prove that they obey a law. So it doesn't make sense to talk about laws of the universe. So philosophy is important because of its unique nature. So testability is a key issue because we are talking about science. To what degree can you test cosmological models? There are major limits to what we can measure or observe. Because of the scale involved, we can't view the universe from a different point in space-time. So we conventionally talk about where we exist in the universe, our galaxy, as here, and the time and now. Now, in the case of the Earth, you can walk all around, you can travel all around the Earth. You can eventually see all the places in the universe. On the case of the Earth, you can eventually see all places on the Earth. You can view all of them from satellites traveling around. We can't view the universe from any other space-time point than the space-time point here and now. So we can only see the universe from one space-time point. I like to have the analogy of an ant trying to discover the nature of the Sahara Desert, and he climbs to the top of a sandhill, and all he can see is all that you can see from that one sandhill. He can't see the oceans, he can't see forests, he can't see anything else. All he can see is sandhills, and we're in the same position in the universe. All cosmological objects, observations see objects as they were in the distant past. We can't see them as they are now, because light travels. We see them by light, which travels at the speed of light. We have to interpret them in the light of any evolution that may have taken place. And we can't see to earlier times than the last scattering surface, as the universe was opaque then. So there are particle horizons and visual horizons that limit the part of the universe we can see. By the way, event horizons are irrelevant to cosmology. So let me show you what I mean by showing you this. This is a conformal space diagram. This is our space. This is time and space. And I've enlarged the spatial scale to make the light cone at 45 degrees. And here, this is our past world line. This is the last scattering surface. This is the beginning of the universe. So this is our world line, and the matter, our world line starts at the Big Bang. Nuclear synthesis took place in the very early universe. Our world line crossed the last scattering surface, and here we are here. And now we can't move off this because of the scale of the thing. We can't see the universe from any different position because if we travel for billions of years, we'd still be in our own galaxy. And we can't travel up and down here because this is 13 billion years. 50,000 years, we'll still be at the same space-time point. So we can only see the universe on one single past light cone. That hits the last scattering surface in a sphere, which is the last scattering surface. And that's what we see in those pictures I showed you. Now, the furthest matter we can see is limited by the visual horizon. Here's matter, which starts off in the Big Bang. This is the world line. We can't see it because our past world light cone runs into the last scattering surface, and light can't travel any further because it can't travel in this strongly scattering space. So this in this strongly scattering domain of the universe. So this matter is invisible to us. We simply can't see it. And this is one of the points about a multiverse. You can say anything you like about the multiverse, but it isn't visible because it's beyond the visual horizon. The visual horizon is the furthest matter that we can see. Furthermore, everything before the last scattering surface is invisible because the universe was opaque. So you can only see things which are this time of the last scattering surface. All of this is hidden. So you can't see the start of the universe. However, there's one point that you can see is that this is our past world line, and nuclear synthesis took place here, and stars formed elements here, which we can measure here and now. So we can do what we call geological kind of observations. If you look at elements here, they all originated somewhere our past light cone, and they give us information somewhere in our past light cone. So, this is a diagram showing you what we can and cannot have evidence about, and we can see the last scattering surface. I've shown you a picture of that. We can't see this galaxy or anything out there. You can't see anything earlier, but we can obtain some data about here through element abundances. Now, there's also what I call a physics horizon. There are limits to the energies we can reach in any particle experiments. Relevant physics in the early universe is untestable. This applies to the inflaton. The matter-antimatter symmetry in the universe depends on physics we can't test. Supersymmetry, supergravity aren't testable, or maybe this is now disproved, and we certainly can't test quantum gravity, string theory, M theory. We don't have colliders which can reach those energies, so there's what I call a physics horizon. Was there a start? And the answer is we don't know. We do not know if there was a start to the universe because that depends on quantum gravity, and we don't know if there was what kind of quantum gravity exists and if it predicts a beginning or not. Classically, we know the required energy conditions need not be true. So the famous singularity theorems depended on energy conditions, and inflation proves that those energy conditions were not true in the early universe. And in terms of quantum gravity, we don't know the relevant quantum theory of gravity. So we don't know if there was a start to the universe. I would guess that there was, but that's not a proof. And what we need to remember, some of my colleagues like to take that the universe was created out of nothing. But before the start of the universe, there was no space-time, there was no physics, and it's very difficult to talk about this. There was no before then. It's a contradiction in terms. So you can draw an arrow pointing to here, but nothing existed then because the whole concept of existence didn't exist then. The universe can't come into existence out of nothing because nothing did not exist, and it's quite difficult to talk about that, but it's very important, the idea that there was no before the beginning. Now, finally, I'm going to talk about some deep issues regarding the nature of the universe, issues that go beyond what science can say. Why does the universe exist? Why does it have the nature it does? Why are there laws of physics? Why are they what they are? And what kind of meaning is there in the universe? And the universe has non-physical aspects that are key to our existence and experience. They should be regarded as deep aspects of the nature of the cosmos. And the basic point, why does the universe exist? It's not a scientific question. Why does it have the nature it does? That's again not a scientific question. Scientific explanation doesn't work before the universe exists. Again, I've explained that before the universe exists, space didn't exist, time didn't exist. And so none of these questions can be answered by scientifically. You can't do any experiments which tell you why the universe exists, why it has the nature it does, or why they're laws of physics, or why they are what they are. No scientific laws apply then. Metaphysical explanation is needed. That is explanation over and above that of physics and testable science. Science takes over only once the universe has come into existence with specific laws of physics governing its dynamics and with specific initial data. So I'm emphasizing that physics is strictly limited in what it can talk about and what it can explain. And it can't explain anything before the universe exists, and it can't explain why there are laws of physics, what their nature is, and so on. Now, there is one thing which is important. Life exists in the universe, and this is what's called the anthropic issue. The universe has a very special nature that allows life to exist, and that need not have been the case. As cosmologists, we can imagine many kinds of universe where life would not have been possible. If either some constant of physics, such as the ratio between the electromagnetic force and the strong nuclear force, or some relation to cosmology, such as the cosmological constant, had been significantly different, no planets at all would have existed. None of the evolutionary processes leading to life would have occurred. So some constants of physics have to be in a narrow range in order that life can exist, and some cosmological features have to be in a narrow range in order that life exists. Our universe is, in the sense, a fine-tuned universe. It has a very special nature. And Luke Barnes is going to talk about that, and it's going to be a very interesting talk. But why is this so? Why is the universe apparently fine-tuned for life? That is a philosophical question, which it's a very interesting philosophical question, but it's not a scientific question. It's a philosophical one. Now, this is what the laws of physics have to be special. And here is the value of the strong nuclear force, which holds nuclei together. Here's the value of electromagnetic force. These are on logarithmic scales. In this region, hydrogen can't form. In this region, chemical reactions are impossible. In this region, stars can't shine. In this region, carbon and heavy elements cannot exist. And carbon-based life is possible in this very small domain of here, of the relation between the strong nuclear force and the electromagnetic force. And so the question is, why did the universe exist in that very small domain? Now, of course, one answer is if it was out there, we wouldn't be here to see it. And so we wouldn't know anything. We wouldn't be asking this question because we wouldn't be here. But we want some other kind of answer if possible. Now, cosmology, if you plot the size of the universe against time, it could, in principle, expand very, very rapidly. It could expand very, very slowly. If it expands too slowly, then it depends on the ratio of kinetic energy to gravitational energy. And in this region here, the expansion is too slow. The universe collapses into a big crunch before life can form. In this part, the life expands very rapidly, and planets, galaxies and planets won't form. In this region, black holes will form, but the big crunch will form before life can occur. Here, it's too rapid, and there simply won't be any planets or any galaxies because the universe expands too rapidly. And structure formation simply won't take place. If you have an exponential structure formation, there is no structure formation. And you have to be in this very narrow range where life is possible. And so this is the second kind of thing. So what we've got is we've got constraints on physics and we've got constraints on cosmology in order that life can form. Now, quite a number of people propose that the reason why this is true is because the multiverse exists. There are other explanations, but I'm not going to go into that because Luke Barnes is going to talk about that in detail. The outcome of cosmology today is that it enables us to exist. And I love this picture. This is an outcome of the nature of the universe. We exist and have this kind of existence because the universe has a very, very special nature which enables our existence. Now, the final thing I want to talk about is underlying everything into existence. The universe is what I call Platonic possibility spaces that underlie exists, and they are what I call the deep structure of the cosmos. Now, there's a whole series of possibility spaces, Platonic possibility spaces, and I'm going to just mathematics, physics, cosmology, biology, thoughts, behavior, and ethics. I'm only going to deal with the mathematics one and the ethics one, but there are possibility spaces for all of these things. For instance, physical possibility spaces depend on the structure of physics, and they're characterized by phase spaces. Cosmology's possibility spaces. I've written a book about phase spaces for cosmology. Biology possibility spaces depend on physics and so on. But any kind, I'm only going to talk about mathematics and ethics. Now, what mathematics exists is determined by our explorations of eternal, unchanging mathematical possibility spaces. They hold everywhere in the universe at all times. Mathematics itself is not a social construct. It is our developing understanding of what is mathematically possible. And that's slightly confusing. I'll explain it in more depth in the next slide. Here's eternal, unchanging truth about the universe, Pythagoras' theorem. You have a triangle, a squared plus b squared is equal to c squared. And this is a very important one, which is true everywhere in the universe, the number pi. The ratio of the circumference to the diameter is pi, which is 3.14159, and so on, as you all know. Now, mathematicians didn't invent the number of pi, they discovered it. And they didn't invent Pythagoras' theorem, they discovered it. And what is very important is to distinguish mathematics itself, the abstract thing, and known mathematics, a social construct, because you'll find some people saying mathematics varies with time. We didn't know about the number pi, and then we didn't. We didn't know about Pythagoras' theorem, and we did. So known mathematics is indeed a social construct. It is what we know about the mathematics itself, the abstract thing. So what I'm claiming is that mathematics itself, mathematic truths are timeless, eternal. They were true at the start of the Big Bang. They're true on the Andromeda galaxy. They're true everywhere in the universe. They may even have been true before the beginning of the universe. What we know varies with time, and there is a projection of mathematics, pi mathematics, which depends on time, and this, what any particular culture or individual knows, changes with time, but the mathematics itself does not change with time, and that is a very important point to make, and that's what I've tried to explain. What mathematics exists is determined by our explorations of eternal, unchanging mathematic possibility spaces. And there's very deep discoveries taking place in mathematics at the moment about the deep structure of mathematics, and very deep stuff is going on. All of this holds everywhere in the universe at all times. And mathematics per se is not a social construct. It is our mathematics which we read about in textbooks, is our developing understanding of what is mathematically possible. And the same applies to physics. The laws of physics are the same everywhere in the universe as far as we're aware. Our knowledge of physics changes with time. So that's the first thing. The second thing, what socially exists is determined by our explorations of eternal, unchanging social and ethical possibility spaces. They are underlain by moral realism, the fact that some social structures and actions are either good or evil as a matter of fact, not as a matter of opinion. Now, this is where I am going way, way beyond physical cosmology. I'm going into an underlying structure which to me is very, very important. To me, it is very important that we should be able to say that if that some things which happen are evil as a matter of fact, not as a matter of opinion, that they can be stated to be evil as a matter of fact. That is the position of moral realism. Morality is real, and some things are good as a matter of fact, some things are evil as a matter of fact. And genocide, for example, is evil as a matter of fact. And what socially is done by our explorations of unchanging social and ethical possibility spaces. So I want to illustrate that now. This is some of the negative kinds of things that can happen. I'm not going to tell you where there is, but clearly something extremely bad is going on. Thousands of people have been killed. The people who did this do not care about human life. This is a completely contrasting thing, and I absolutely love this picture. This is a wonderful picture of a little guy looking with total trust and faith at someone who's doing the best he can for this little guy. And the contrast between these two pictures couldn't have been more dramatic. So it is crucial to be able to some action as evil as a matter of fact, not a matter of opinion. Examples are genocide, apartheid in my own country, and killing or torturing people for fun. This is the position of moral realism. Moral realism says that you can label those evil as a matter of fact, not of opinion. And I propose that moral realism is part of the deep, non-physical deep structure of the cosmos. It is true at all times and places, everywhere in the universe. The fact that things can be evil is the same on planets anywhere else in the universe. It does not depend on being on this particular planet. And again, exactly the same thing is true. You need to distinguish morality, what is good, the abstract thing, the thing which is an absolute fact at all times and places, and our ethical understanding. Different societies have different understandings, and they change over time. And part of the history of humanity is people changing their view about what good and what bad and what evil is. So it's exactly analogous to what happens in mathematics. Morality, what's good and what's evil, is the same at all times and places. There's a projection of an ethical projection. What any particular society or person understands varies with time, place, and society. It's in parallel with the difference between mathematical understanding, a social construct, and mathematical itself, unchanging Platonic reality, which is the same in the universe at all times and places. And this is my final thing I want to say. So how do you characterize this relation between good and evil? And what I propose is that there is a spectrum from coercion to kenosis, which takes values from -5 through 0 to +5. And I'm going to briefly explain that. -5, you're willing to indulge in genocide. You're willing to wipe out a population, wipe out every single member of that population, genocide, which has taken place in various cases. The one prime example being what happened in Germany during the Second World War. Level -4, you're not going to try to wipe out people, but you're willing to kill them and torture them in order to attain what you want. -3, you're willing to cause them physical harm, not going as far as killing them or torturing them, but you're very willing to cause them physical harm. -2, and So that's -5, that's -4, -3, -2. You're willing to undermine them, but not actually causing the physical harm. Indifferent, you don't care one way or the other. Here is what's called getting to yes. I'm willing to work with you to get something together for us. The golden rule, I will do for you what you would like to do for me. This is the role of forgiveness. I'm going to forgive you for what you've done, even though you caused me harm. This is Nelson Mandela and Desmond Tutu. And what is called kenosis is the idea that I am willing to suffer on your behalf, even if you are your enemy. And any ethical position can be placed somewhere on this scale, and you can determine where people are by how they behave. And it is empirically determinable. It's not just a matter of opinion. Right at this moment, there are people being killed in the Persian Gulf because certain people are willing to kill in order to gain what they want, and they do not care how many people they kill. It's empirically determinable that's the case. It was empirically determinable that the Nazi regime tried to wipe out the Jews as a whole. And so there's nothing, it's not a matter of opinion, it's a matter of determining what happened. The term forgiveness, you can determine that Desmond Tutu and Nelson Mandela ran the whole, they ran their whole political and moral campaign on the basis of forgiving people for what they had done. There was a Truth and Reconciliation Commission, which was based on this. So what I'm saying here is that the deep structure of the universe includes these kinds of things that I am now talking about. The universe is not restricted only to physical interactions. It includes the kinds of things which I've been talking about in this last section, the way people interact. They have to exist, so there has to be a possibility of existence. But once they exist, I'm saying that this scale, it can be applied to people, it can be applied to institutions, it can be applied to countries, and it can be applied to anywhere, anytime. And you can determine by empirically, and and what I'm saying is anything to the it scales -4 or -3 is evil as a matter of fact, and anything to the right of 4 and 5 is good as a matter of fact. And so that's where I end.
Thank you very much, Professor Ellis. And this lecture, it is both scientifically rigorous and philosophically expensive. Um I am feel like I what I want to say that most of the lectures what we go through we understand through our mind, but this lecture what I personally feel that it should be feel. So thank you so much for this deep discussion, and the big picture is actually bigger than for us to perceive, and you so nicely described the fundamental issues of cosmology. It's a classical presentation, sir. Um, Now we'll go towards the question and answer session. Okay, so the first question from Professor Tejinder Singh, Tata Institute of Fundamental Research. It is said that inflation predicts multiverses, each with its own laws. The enormous landscape of string theory, vacua, is invoked as supporting evidence for inflation and multiverses. Do you agree with this? Or is this telling us that inflation and string theory are incorrect descriptions of physical reality?
Hi, Chitendra. Nice to hear from you. Um, yeah, there are many versions of inflation do predict multiverses. Now, that is true. But the first problem comes, but there's over 200 versions of inflation, and not all of them predict multiverses. But nevertheless, some of them do. Now, one of the points is spatial homogeneity. If the universe is spatially closed, then that doesn't necessarily work. But the deeper point is the landscape of string theory vacua is invoked. Now, there is no evidence whatever that string theory is true. And in fact, it requires supersymmetry. And as far as I can tell, there's evidence against supersymmetry at the present time. So, but the difficult point is, supposing we believe in string theory, suppose supersymmetry is true. The question is, how do you get different physics in the different multiverse domains? And I know that there is a mechanism that I think it's the KKLT mechanism, which I'm not an expert, but that seemed to me a very, very a dubious thing. But I want to make one point about this, is that that claim that you get the multiverse, it depends on which of the models is correct, which potential is correct. And supposing that that you have one which creates a multiverse. Now, you have to have a multiverse which allows life to exist in at least some of its universe domains. And what you've done from a philosophical viewpoint, you haven't solved the anthropic issue. You've just lifted it one level up, because the question then is, well, why is my multiverse one that admits life to exist? I can create for you a multiverse which does not allow life to exist. So it is a possible solution if you believe in string theory, and if you believe in a KKLT mechanism or something similar, which is a lot of very big ifs, particularly given that supersymmetry doesn't seem to be true. But the further issue then is why does that particular potential hold in your multiverse?
Okay, thank you, sir. Proceeding to next question. Wonderful lecture. Really provided a big picture. You mentioned about spaces of thoughts. Could you elaborate on it?
Yeah, there's a wonderful book talking about this. It's called The Library of Babel by John Louis Borges. And the point about this is that you need to start thinking about thoughts, and what you can do. The Library of Babel is a wonderful novel by a guy called Borges, and he envisages a library, a huge library, which contains all possible books that can be written in the universe. So you can say, hang on, wait a minute, there's an infinite number of books, but there aren't. And the reason is the following. It's a very interesting reason. If I start talking to you, my sentence must have a finite length. And the reason is because you must remember the beginning of the sentence by the time you reach the end. Now, what that means is that a sentence must be, we have limits in short-term memory, and that limit is 7. And there's a famous paper called The Magic Number 7 pi to minus 2. If a sentence is more than 7 times 7, 7 slots, each with 7 words, you can't remember it. By the time you reach the end of the sentence, you can't remember the one that began. So in other words, any possible sentence which conveys a coherent thought has a maximum length, and I'll be quite generous. Let's say it's 490 words. Okay. Well, what that library is, the Library of Borges, it's a library that contains all possible books with all possible thoughts, and in all possible languages. It's actually really worth reading that book. And the Library of Babel contains all possible thoughts. And And those thoughts contain thoughts. Most of the books in the Library of Babel are complete nonsense, but they contain all possible books that are not nonsense and all possible books that are slightly different from the ones that have been written. And the key point about this is that this is a finite number. It's a finite space. It's not an infinite space. As soon as you start the word infinite, then things get difficult. But the number of possible thoughts is finite. It's a very, very large number. It's a huge number. But nevertheless, what I claim is one of the possibility spaces is a space of all possible thoughts, and that is a finite space, and that again has been the same since the beginning of time. Now, once you start looking at this, you realize there's a similar space, a space of all possible images. And we're seeing that nowadays because any picture, such as a standard digital picture, has got a finite size. It's quite a large size. It's I can't remember how many bits it is, but any picture. And so you can have a space of all possible images because it's a finite space. And it's the same for music. You can have a space of all possible tunes and all possible songs. Each of these have finite possibilities. So underlying what actually exists, there's a space of possible books, which contains all possible thoughts. There's a space of all possible images and a space of all possible music.
Okay, thank you, sir. Moving to the next question. So this is from Inyavan. Uh, Modern cosmology explains the evaluation of the universe through well-tested physical laws such as general relativity. Yet the large-scale structure of the universe still depends strongly on its initial conditions. From a fundamental perspective, do you think the initial conditions of the universe should themselves be regarded as something that requires a deeper physical explanation, or might they simply be bureaucratic facts about our universe?
That's a very good question, a very nice question. Now you run into the problem I talked about, the uniqueness of the universe. You can make any theory about initial conditions you like, but you can't test it because there's only one universe. So you can't run different universes and test them. You can't observe universes. So make any such theory you like, and you can't test it. So in that sense, you can make such a theory, but it's simply non-scientific. So now, Roger Penrose has tried to do such a theory with his conformal condition at the Big Bang, and he is very well motivated. And Stephen Hawking has had a very interesting thing with his no boundary conditions. Now, just to comment on each of these. Roger Penrose then goes into his conformal cyclic cosmology, and I just don't happen to think that's a good way, as a way of trying to explain that initial condition, and I don't think that works for reasons I could explain. And Stephen Hawking's one depends on the idea of a wave function of the universe, and I don't happen to believe there is such a thing as the wave function of the universe. There's a whole theory of quantum cosmology which depends on the concept of the existence of the wave function of the universe. Before you have a theory of the wave function of the universe, firstly, it depends on the Wheeler-DeWitt equation, which is an ill-defined equation which has not been tested and cannot be tested. And secondly, I simply don't believe that there is a wave function of the universe, and I could go into that. I've written a paper about this. The idea of a wave function of the universe is that there is one single universe which covers the whole universe. Now, the problem with this is that a wave function evolves linearly. The Schrödinger equation is linear, the Dirac equation is linear, Feynman's path integral is a linear structure. And I could explain all of that. And so my resolution of this is to say all of these ideas are mistaken because there does not exist a single wave function of the entire universe. What does exist is local wave functions. And the entire universe is covered with local wave functions, each of which locally obeys the Dirac equation or Schrödinger equation. And this is in complete analogy with general relativity, when the key to solving the large-scale structure of space-time was to understand that in general, you cannot use a single coordinate system to cover the whole of space-time. You need an atlas of many, many coordinate systems in order to discover space-time. And I believe exactly the same is true for quantum physics. You need an atlas of local wave functions, not a local wave function, and that immediately solves a great many problems about cosmology.
Okay, thank you so much, sir. Thank you for this these questions and answer session. And I would like to once again express our sincere gratitude to you, sir, on behalf of the Bhaktivedanta Institute and all the audience. Thank you, sir.
Thank you so much.